Let's move on towards our discussion on matrices. Every square matrix can be uniquely expressed. So every square matrix, you already know what is a square matrix. You have already learned in the previous lectures what is a square matrix. Okay, so every square matrix can be uniquely expressed. What does it mean by uniquely expressed? Uniquely expressed means that there will be only one representation. What does it mean by uniquely expressed? Uniquely expressed means that only one type of representation is possible. Okay, so can be uniquely expressed as the sum of a symmetric matrix and a skew symmetric matrix. So suppose we have a matrix A, okay, and it is a square matrix. Suppose A is a square matrix, then there will be a symmetric matrix and there will be a skew symmetric matrix. Okay, so this matrix A, which is a square matrix, by the way, this is a square matrix. It can be uniquely expressed as a sum of symmetric matrix and a skew symmetric matrix. Okay, and uniquely expressed means that other representation is not possible. Suppose this is first skew symmetric matrix and this is second this is first symmetric matrix and this is second skew symmetric matrix, then it can be only expressed, it can only be expressed as s1 plus ss2. Okay, other type of representation s2 plus ss3, other type of representation is not possible. Okay, other type of representation is not possible, that is the meaning. This type of representation will not be possible, this will not be possible. Okay, so that is the meaning of this statement. Okay, now let A be any square matrix. Suppose A is any square matrix, then we can write A matrix to be equal to half of A plus A transpose plus half of A minus A transpose. How did we write this? So the thing is that if you expand this, half A plus half A transpose plus half A minus half A transpose, so this term, this particular term and this particular term will cancel out, and half A plus half A will give you full A. Half A plus half A will give you full A. So that is why it can be expressed. It can be expressed like this. So now this, let us assume that this is equal to P. So we have represented this by P, and suppose this is equal to Q. So we have represented it by Q. So P is equal to half of A plus A transpose and Q is equal to half of A minus A transpose. Okay. Now we will prove that P is symmetric and we will prove that Q is skew symmetric. We will prove that P is symmetric and Q is skew symmetric. That is what we need to prove. So P transpose, if we take the transpose and it comes out to be equal to P, then it will be a symmetric matrix. Okay, so let us take P transpose. We took P transpose. So instead of P, we will write this stuff. Instead of P, we will write this stuff, that half of A plus A transpose. So half of A plus A transpose, then we will take its complete transpose. Okay, now this 1 by 2 will come out of the transpose. 1 by 2 will come out of the transpose because it is a constant value or a scalar. So scalar will go outside and only transpose will be applied to this term. So transpose will be applied to only this term. Now we know this very well, that A plus B complete transpose, A plus B complete transpose, A plus B complete transpose is A transpose plus B transpose. So A transpose is as it is A transpose transpose. Okay. Now transpose of transpose is the same matrix once again. So A transpose transpose will be equal to A and A transpose will remain as it is. Now you have a look at this, that P is equal to, we already know that P is equal to what? P is equal to this entity. P is equal to this entity, half of A plus A transpose, and we have got half of A transpose plus A. Addition is commutative, so we can write A first and A transpose later on. Okay, so we have written half of A plus A transpose, which is equivalent to this. Okay, so half of A plus A transpose, but half of A plus A transpose is equal to P, so this entity is equal to P. So we have successfully shown that P transpose is equal to what? It is equal to P. So this means that P is symmetric matrix. What does it imply? It implies that P is symmetric matrix. Now we need to prove that Q is skew symmetric. We need to prove that this is skew symmetric. So let us prove that is skew symmetric. So let us take its transpose and let us prove that it is skew symmetric. So Q transpose, Q you already know, half of A minus A transpose is equal to Q. So let us take its complete transpose. If it comes out to be equal to minus Q, then we can be sure that Q is skew symmetric. Q will be skew symmetric if this particular entity's transpose comes out to be equal to minus 2, then Q will be skew symmetric. So half of A minus A transpose complete transpose, half will come out okay, by this particular property. Even there is no need to write this property. There is no need to even write this property because it is quite self-explanatory. But still, I have written it over there. Okay, so half will come out. Then again, one property will be used. Okay, its transpose will be there. Half will come out. Its transpose will remain. Then this transpose will go over here, and this transpose will also go over here. So A transpose as it is, then minus A transpose transpose. Okay. Now transpose of transpose is equal to the matrix itself. When we take a matrices double transpose, it becomes the same matrix. Okay. So A transpose has come from here, it went here, and it became like this. If from here it went there, it became like this. This became like this. This remained as it is. Now take minus sign common out of this. So as soon as you take minus sign common over here, you will get minus 1 by 2, and this minus A will become plus A, and this plus A transpose will become minus A transpose. Now you already know that this entity is equal to Q. This particular entity without minus sign is equal to Q, but with minus sign it will be equal to it will be equal to minus Q. Okay, so Q transpose has come out to be equal to minus Q, as Q transpose is equal to minus Q. So Q is skew-symmetric matrix. Clearly Q is skew-symmetric, and we have proved that P is symmetric. We have proved that P is symmetric. Also we have proved that Q is skew-symmetric. Now we have proved the existence. Till now what have we proved? We have proved the existence. Okay, we have proved the existence, but we have not proved the uniqueness. So we have proved that A is equal to P plus Q, where P is symmetric and Q is skew-symmetric. We have proved this, but we did not prove that it is unique. This P and this Q is unique. That is, only one representation is possible. Only one type of representation is possible. That is, P will be unique and Q will be unique. This fact we have not proved till now. We have just proved that they exist. They exist is what we have proved, but the uniqueness we haven't proved. Okay, so let us prove the uniqueness. Let A is equal to R plus S be another representation. So we already know that A is equal to P plus Q is one representation, and we are, in order to prove uniqueness, we are assuming that R plus S is another representation, and R is symmetric because we are taking R corresponding to P, we are taking R, corresponding to Q, we are taking S. So as corresponding to P, you are taking R, so R will be symmetric, and corresponding to Q, you are taking S, so S will be skew-symmetric. So R is symmetric, that implies R transpose is equal to R, and S is skew-symmetric, so that implies S transpose is equal to minus S. S is skew-symmetric, so S transpose is equal to minus S. Now we need to show that R is equal to P. Okay, if they are unique, then R will come out to be equal to P, and S will come out to be equal to Q itself if the representation is unique. Okay, once again listen, if the representation is unique, then R will come out to be equal to P itself, and S will come out to be equal to Q itself if the representation is indeed unique. So let us prove the unique representation. Now A is equal to R plus S. Right now we have assumed just now A is equal to R plus S. Let us assume this is equation number 2. Now take transpose on both sides. So A transpose will be equal to R plus S complete transpose. Now A transpose remains as it is, and this A plus B complete transpose property, transpose will go with R, so it will be R transpose. Transpose will go with S, so it will be S transpose. Okay, so A transpose is equal to, now you already know that R transpose is equal to R. R transpose is equal to R because R is symmetric. R transpose is equal to R because R is symmetric. And similarly, S transpose is equal to minus S. S transpose is equal to minus S because S is skew-symmetric. Okay, so R transpose is equal to R because R is symmetric. S transpose is equal to minus S because S is skew-symmetric. Okay, so A transpose came out to be equal to R minus S. Let us assume this is equation number 3. Now add these equations 2 and 3. So what will you get? If you add 2 and 3, S and S will cancel out. S and S will cancel out if you add 2 and 3. So S will cancel S, and 2R will be there in the right hand side. 2R, R plus R will become 2R, right? R plus R will become 2R. S and S will cancel out, and A plus A transpose will be on the left hand side. So A plus A transpose on the left hand side. Okay, R and R becomes 2R on the right hand side, S and S cancel each other. Now this R comes out to be equal to, if you take this 2 to the left hand side, then R will become half of A plus A transpose. But half of A plus A transpose is P itself. Half of A plus A transpose is P itself. It means that when we assumed another representation, when we assumed another symmetric matrix, it came out to be equal to the first matrix itself. When we assumed another symmetric matrix, it came out to be equal to the same symmetric matrix as before. So uniqueness of symmetric matrix is proved. Okay, now let us prove the uniqueness of skew-symmetric matrix. Let us prove the uniqueness of skew-symmetric matrix. Now subtract 3 from 2, 2 minus 3, 2 minus 3, okay, subtracting 3 from 2, that is 2 minus 3. So when you do 2 minus 3, what will happen? A minus A transpose will be on the left hand side. So A minus A transpose on the left hand side. On the right hand side, R plus S minus R minus S. What will happen on the right hand side? On the right hand side, R plus S minus R minus S will happen on the right hand side. So R plus S minus R, this minus sign will go inside the bracket and minus R plus S will become, okay, and R will cancel each other, and S plus S will become 2S. Okay, so it will become 2S. So it became 2S after taking 2 minus 3. A minus A transpose is equal to 2S. These R and these R cancel each other. So A minus A transpose is equal to 2S. Now this 2 can be taken to the left hand side. So S came out to be equal to half of A minus A transpose. But half of A minus A transpose is what? Half of A minus A transpose is Q itself. It is Q itself, right? So S is equal to Q. We have successfully shown that S is equal to Q. It means that if when we take another skew symmetric matrix as the representation, it comes out to be equal to the original representation itself. So the R and S, we had assumed that R and S are another representation, and those another representation came out to be equal to the original representation, that is the same representation. So uniqueness is proved successfully. Hence every square matrix can be uniquely written as the sum of symmetric and skew symmetric matrices. So every square matrix can be uniquely written as the sum of a symmetric matrix and a skew symmetric matrix. We have successfully shown this particular fact. Okay, so this fact has been successfully shown. Now the lecture is going to end now. One end screen will appear over here, and on the end screen you will see a playlist of matrices. So go and watch that matrices playlist and enjoy the lectures. Okay, one end screen will appear over here. Thank you very much.